So last time there was the, well, let's recall the basic definition we're saying is A has got a smaller size than B if I can inject, if there's some function which takes A into B one-to-one. This says there's a bijection between them. And this is saying that I can inject A into B, but not vice versa. And the Counter-Schroeder-Bernstein theorem this says if I can inject A into B and I can inject B into A, then A is bijective with B. So it showed how to take two one-to-one functions, f and g, here, and construct one bijection, H, there. And then we defined something that said set X is countably infinite if X is bijective with omega. We say X is just countable, so closely related, but don't get confused by it, means that I can one-to-one map X into omega. So countable includes finite. But countably infinite, of course, emphasizes the infinite part. It's bijective with omega. And let me just see for a moment. We saw also how any subset of a countable set is countable. That was lemma 415. Okay, so what one can then show from this is, well, what one can then, continuing looking at these properties of countability and being denumably infinite and so on. Something like exercise 4.11.1. Show if you've got a non-empty set, if and only if there's an onto map. So countable includes finite. It's defined by saying there's an injection into omega. Okay, show that that's equivalent to being an onto map from omega back onto X. So it's a question of working with the definitions there. Right? Okay, so what would you do here? Okay, it's an if and only if here. We're told that X is countable. So I've got a map from X into omega, which is 1 to 1. So implicit in the notation there is that G is going to be 1 to 1. And we need an onto map F. So we could use G, except that, of course, the range of G is not all of omega, right? Necessarily. Right? If it was all of omega, then we are done. We could just use G to the minus 1. But it may not be all of omega. So what we do then is just define some object in G for F to send M back to for those things that are not in the range of G. Some fixed X naught in X for any M that's not in the range of G. And F of M would just be G to minus 1 of M otherwise. Okay, so the F here doesn't have to be 1 to 1 or anything, just has to be onto, and that's what we've done. So now we've got, we want the reverse direction. So there's an onto map, and we need to show that that means that X is countable. So again, going back to the definition, it means I need a 1-to-1 map going back. So for any U in X, okay, let A of U be those things in omega, those n's in omega. Sorry, the n's, let's say m's in omega here, such that F of M is U. So F is onto, it may send a whole bunch of things, right, to the same object U in X. So AU tells me what that bunch is. Now, because F is onto, for every U in X, this is non-empty. As F is assumed onto, for all U in X, A of U is not empty. And for different things, A and U and A and V are disjoint. So now all I have to do is just use the fact that these are numbers and we've got a well ordering for them. So we just use the fact that the naturals are well ordered. And define our one-to-one function So we'll just say let h of u, just to be consistent there, let h of u to be the minimum of a of u. So we just pick one thing from a of u to send u to. So then h is going to send x 1 to 1 into omega. And it is 1 to 1 because these are disjoint. Since, as we just said, these are all disjoint. Okay, so, I mean, that completes that direction. So the point of the exercise is to get familiar with these two definitions of countable and being countably infinite. And it's just a question of slowly thinking through what the definitions are and putting down some logical steps about how we can justify that.
Sorry, could you write down the definitions of one-to-one and onto, if that's okay?
One-to-one and onto?
Yeah, just like very explicitly.
Okay. As you will have learned in first year foundations and proof, f is 1 to 1. Okay. Here, if for, let's say, for any x and y in A, if x is different from y, then f of x is different from f of y. Okay, so it sends different things to different things. F is onto, it's going from A to B. If I say for all u in B, there is a v in A such that f of v equals u. So everything in B comes from something in A, which is what this is. For all u in B, there is a v in A such that f of v equals u. Okay?
Thank you.
Right. Okay, so let's continue with some more of these exercises. Just look at seeing what they say. Lemma 416 comes next. Any subset of a countable set is countable. Well, again, just have to keep clear what it means to be countable. If a set is countable, it means there's a one-to-one map from the set into omega. So actually the lemma is quite trivial, because if I take a subset of the domain of that one-to-one map, the function restricted to that subset is still 1 to 1, and it still goes into omega. So actually, this is just an exercise. Just look at the definition. I'm sorry, I've jumped from 416 and I wrote down 415. 415. Okay, 416. So I take two countably infinite sets. Show that their union is countable, countably infinite. So again, remember, get in your heads the distinction between countable and countably infinite. Here, this countable can include finite, but this specifically, kind of in the wording, ensures that you're talking about something that's infinite there. Okay, so again, this is an exercise. What do you start with? I think this is exercise 414. So now you just have to think about what it means here, right? To say that x and y are countably infinite means you've got h, a bijection between omega and y, and g, a function and a bijection between omega and x, and you need to design a bijection between omega and x union y.
Sorry, going back to the proof in the left direction, when you said as f is assumed onto, and then isn't there just a definition of injectivity as opposed to surjectivity? Where
So which direction are you talking about? Right to left here?
Yeah, that one, and then just the line below that, yeah.
F, which is going from omega to x, is assumed to be onto.
Yep.
Yes.
Okay, but then the condition that follows with the intersection, isn't that the one-to-one condition?
No, because the things that get sent to you, I mean, a function is single valued. Even non-one-to-one functions are single valued. A function can't send an m to two different things.
Oh, okay.
So if a function sends m to u, it can't send it to v if they're different. It's nothing to do with one-to-oneness. It's just to do with being a function.
Okay, thank you.
Yeah, okay. So in here, we've got bijections between omega and y and omega and x. And what we need is a bijection between omega and x union y. Right, so a bijection here. Okay, so I'll leave you to think up something about that. The point is, you see, of course, that x and y might not be disjoint. I mean, if they were disjoint, I could send the evens to y and the odds onto x and combine that to give me an L, right? But x and y need not be disjoint. Maybe non-empty. Sorry, yeah, x intersect y may be non-empty. So you need to think up a trick about how to define some L like this. Right? So it needs a small trick. So a small idea is needed. So I'll leave that. Okay, so if I've got two countably infinite sets and their union is countably infinite, I could keep repeating this argument and then show by induction. Maybe I've got sets x1 up to xn countably infinite. Then their union is also countably infinite. And the next question that arises is, suppose I've got countably infinitely many sets x, is the union then countably infinite? I might be for every n, I've got xn, which is countably infinite. Then I put the union together. I'd like that to be countably infinite as well. So we'll see under conditions that that's true. Well, exercise 412 says show that there's a bijection between omega and omega cross omega, this Cartesian product. Right? And indeed, actually, the hint gives you the answer. Right? So you just look at the function in this direction here, and it just sends pairs f of mn, if I've got this right, so we call this a pairing function. It's a nice one-to-one onto map from all the pairs onto omega. So f is a bijection there. Here. Okay, check that you see this. We also use as a bit of notation the kind of unpairing functions. So unpairing functions. So in this context here, suppose f of fm, let's call this number here t. F of m n equals t, then the left-hand element, so to speak, of t is going to be m, and the right-hand element of t here is going to be n. So this little function here just takes the natural number and decodes what power of 2 divides u plus 1. Right? And what u1 does is take u and it adds 1 and divides it by the largest power of 2, and that's the odd number 2n plus 1, and it returns n. So those are useful functions to have. show that Z and Q are countably infinite. Okay, so again, countably infinite means bijection with omega. So what are you going to do? Clearly both sets are infinite, but we need a bijection. Okay, so let's just consider Q. Okay, so let F be this function here that's above. So this is from the last exercise here. So of course, F to the minus 1 takes omega back to omega cross omega. So define H omega cross omega to Q. So now we'll say H of any number P is 0. Here, we'll send those to 0. I just need to kind of cook something up. I'll send the evens, 2 P's together with a Q to be on Q. For Q not 0. And for the odds, send that to minus P on Q. Again, Q non-zero. So I look at F to the minus 1 followed by H. This then is onto Q. Okay. So this shows that Q is countable. And we see that it's infinite. But being countable and infinite is countably infinite. You could say, oh, why is Q clearly infinite? Well, infinite means not finite. You're not bijective with a natural number. Well, Q contains the infinite set of omega, all the natural numbers. Okay? So as omega is infinite, Q is not finite. Right? So I've got the Q is infinite and it's countable. Right? That's what this says. So it's countable and infinite, but that's equivalent to being countably infinite. Q is countably infinite. If you look back at what that exercise says, if you establish that something is infinite and it's countable, there's a bijection. So that would finish that slightly harder part of the exercise. For Z, a much easier idea is needed. You can just write down a bijection between omega and Z straight off. It's just a little trickier with Q. Okay, let's look at exercise 415. So it's about just sets in general. And you're asked to show various things are bijections. I'll just do one. This is part 3. Let's just see what it says. So recall, b to the a is the set of functions from a into b. So this is the set of functions from x into this Cartesian product. And you're asked to show that this is bijective with the Cartesian product of two sets of functions. So these are different things. Right? This is ordered pairs, both elements of the ordered pair of functions. This is a function, which indeed happens to be a set of ordered pairs. So what you have to do is to actually concretely, what the exercise asks you to do is concretely find a bijection, right, which is going to do this. Okay, so we steam ahead and try and find something. Right? So I'll pick a function in here. How can I associate a pair of functions over here with it? Well, here this is supposed to be two functions, into one into y, one into y, one into z. So we just take the function here and just split it. Right? So I take a function over there on the left-hand side. Right? And I'll define a map G going from here to here. G of f. And that is going to be two functions, little gh here. And that'll be in the right-hand side. So an ordered pair of two functions. And after all, what does f do? It takes things in x and it returns an ordered pair, a left thing and a right thing here. So I use those unpairing functions, which I just mentioned. So I'll set g of something in x to be the thing that f sent that x to, but just the y part. which is the left-hand part of this unpair here. And likewise, h of x will be f. Yeah. Again, f will send x to a pair of things, and what h does is pick out the thing in z, which is just what we want here. Now, f, I think you can then say, then that big G is clearly one-to-one. Because if I've got two different functions here, they must do something different somewhere or other. Two different functions, right, must send some particular thing in here to two different objects in y cross z. So I think you can just say G is clearly one-to-one. Okay, if you really want to spell it out, if I've got f different from f prime, then for some u in x, f of u is different from f prime of u, because they're different functions. So if f of u is, let's say, gh, and f of u prime is g prime h prime, one of g and g prime, or h and h prime, must be different from the other, right? Because these are different things. So g of f is different from g of f prime. One of these g prime, h prime pairs are different, at least one. So g of f can't be the same as g of f prime. So it's one-to-one. But this is supposed to be a bijection. So we need to check as well that it's onto. So we just do this check here. We just say something about it at least, right? Okay, so I pick something in here, So I pick something here in this right-hand side. It's a pair GH, like this. I just need an F, which the big G is going to pick out this GH. Well, you just put the two pieces together, put the two G and H's together. So we'll define f of x to be the pair gx, hx. Here, then it's doing the right kind of thing. It's taking an x and it's returning an ordered pair, first thing from y, second thing from z, here, which is this. So you can then check that our definition, g of f is gh. By design, by construction. Right? So it's onto. And the other parts of the exercise ask you to do, and I'll be setting some of these, ask you to do things for other similar bijective sets here. Okay. So 417. Let X be an infinite set. Right? No assumption about it being countable or not. Right? It's just infinite. And we've got a well ordering of it. Then it's got a countably infinite subset. Okay, again, countably infinite means bijective with omega. So we know that much about X. So, I mean, the picture is, here's X as this kind of amorphous group of things. And the only other thing I know about it is that I've got this well order on it. So countably infinite subset. Well, we just pick out a countably infinite subset, which is clearly bijective then with omega. So we'll let X0 be here. The R least element of big X here. And we define by recursion, we just keep going. Xn plus 1 to be the R least element of X when you've removed the first n plus 1 things we've chosen. Right, so if this was here was Xn, we've chosen these, so we just choose the next thing in the ordering R. So it's simple. And then clearly what we've got here is an omega sequence, so it's a set bijective with omega. Right? It's obvious, it almost doesn't need saying. Right? But I couldn't have said that argument without knowing that R well-ordered X. Otherwise, how am I going to do this recursion? I can't do it, right, without this R mechanism that allows me to keep picking the next thing. Right? So knowing that sets are well-ordered is terribly useful. And in fact, we're going to assume that as part of our set of axioms about sets. We'll see towards the end of the course that this is equivalent to something called the axiom of choice. But we'll adopt this because this is actually more useful in our context first. I'm going to call it WP. Any set can be well ordered. Then there is a well ordering of X. I mean, you might say, well, why is this necessary? But for example, the natural numbers, they kind of come with a well ordering. It's the epsilon is less than, it's kind of built into the definition, the ideas anyway, of natural numbers. But for any amorphous set, there's no particular a priori reason why there should be a well ordering of it. So this is an assumption that's being made about all sets here. So it is an existence assertion about sets, right? Okay, so I'll finish that with that this time. Next time we'll again continue going through the notes here. We'll prove that assuming the double ordering principle, every countable union of countable sets is countable. And then we'll start defining cardinal numbers in the next section 4.2. Fine. If there are any questions, do send them through.